that will be u dt by dx plus v by dy, that is equal to k, oops, there should be a rho Cp here, k into d square t by dy square. I missed out a rho Cp in my earlier model that I wrote, so there should be a rho Cp in the front, okay. So that will be, so the scaling will be u into u star, okay. So now I said that we scale it with T infinity, but remember when we actually wrote the heat transport coefficient, right, when we define heat transport coefficient, we said that it is always a function of the temperature of the surface. So now it is better to incorporate the temperature of the surface also in the scaling, okay. So the better way to define a scaling for the temperature is Ts T minus T surface divided by T infinity minus T surface, okay. So that is a better scaling to introduce, and so if we introduce that scaling, it will be T infinity minus Ts rho Cp into dt star divided by L y star plus u into v star T infinity minus Ts divided by L into, oops, should be x T star by dy star, okay. That should be equal to k into T infinity minus Ts divided by L square into d square T star by dy star square, okay. So now if I do the algebra, so that will become u star into dt star by dx star plus v star dt star by dy star, that should be equal to, so the T infinity minus Ts will cancel out, that will cancel out, okay, and so you will have k by rho Cp into 1 by L square, and so we get L by V from the other side, okay. So, it will be L by U into d square T star by dy star square. What is k by rho Cp? It is 1 by, k by rho Cp is thermal diffusivity, right? Rho Cp by k is thermal diffusivity? No, it is k by rho Cp is thermal diffusivity. So, this will be alpha divided by u into L d square T star by dy star square, okay. Is it dimensionally correct? No? Why? What is alpha? What are the units of alpha? Meter square per second, u into L is meter square per second. So, when you non-dimensionalize, all the terms should have no dimensions, right? So, it is fine. Okay, what is alpha by UL? What is alpha by UL? Prandtl number? Is it? It's Peclet number. Okay, so what you can do is you divide this by nu, okay. What is nu? Nu is the kinematic viscosity multiplied by nu by UL. What is alpha by nu? Okay, so this is one by Prandtl number. What's nu by UL? 1 over Reynolds number, right? So this is 1 by Prandtl number into 1 by Reynolds number. This is 1 by Prandtl number, not Prandtl. Okay? Yeah? 1 over Peclet number. Prandtl into Reynolds is Peclet number. Anyway, Peclet number is not important now. We will actually look at it when we talk about mass transport. We will actually see some importance of Peclet number there. So this is 1 over Prandtl into 1 over Reynolds number. Okay. So the model equation will be U star dt star by dx star plus V star dt star by dy star, that's equal to 1 by Prandtl number into Reynolds number d square t star by dy star square. So Prandtl number is alpha by nu by alpha. Nu is momentum diffusivity, alpha is thermal diffusivity, right? So this is momentum diffusivity divided by thermal diffusivity. So that's what is Prandtl number. So it tells you, supposing if there is simultaneous momentum and heat transfer, it tells you what is the extent of momentum diffusion versus the extent of thermal diffusion, and both of these are happening simultaneously. Okay. What will be the mass balance? Non-dimensional form. Can we guess? I want to do the same non-dimensionalization for mass balance also, right? You've done for x and the y component momentum balance, you've done for the energy balance, I want to do it for mass balance also. Can we guess from here? Yes or no? Should be, because the energy balance and mass balance, they have similar structure. Remember in last lecture I told you that these three balances, they actually have very similar structure. So if you know one, you should actually be able to guess what the other one is. Okay. So the mass balance, non-dimensional mass balance will be U star dCA star by dx star plus V star dCA star by dy star, that should be equal to, so let's start from the first one. Okay, let's not worry about Prandtl right now. So instead of alpha it is, its mass diffusivity, so that will be dAb divided by UL into d square Ca star divided by dy star square. Okay. So what is dAb by UL? So very similar to what we did here, we multiply and divide by the kinematic viscosity. So that will be dAb divided by nu into nu by UL. So that will be 1 by Schmidt number into 1 by Reynolds number. Okay. So this term here is 1 by Schmidt number into 1 by Reynolds number. Okay. So if I write down all the balances, so you can see that there is a strong similarity between the heat transport, mass transport and the momentum transport. Okay. So there is one caveat to it, which we will see in a short while. So if you see the momentum balance, it's U star du star by dx star plus V star du star by dy star, that's equal to minus dp star by dx star plus 1 by Reynolds number into d square u star by dy star square. Okay. And the energy balance is d star u star dt star by dx star plus V star dt star by dy star, that's equal to 1 by Prandtl Reynolds number d square u star t star by dy star square, and you have u star dCA star by dx star plus V star by dy star square. Okay. So if you look at the first two terms in all three equations, they are very similar, right, except that here u is replaced by t and here it is replaced by Ca. Similarly, the second order derivative term also, you can see that they are similar. What about dp by dx? So if I have to say that these three equations are similar, then I need to know something about this, right? So if that's a function of position, if it's a function of position, then I can't say that these three are similar. So only if I know what is dp star by dx star, then I should be able to say that these three are similar equations. Okay. So if I know what dp star by dx star, which is actually not a, okay, so note that I am pumping the fluid, right? So it's a forced convection where I am pumping the fluid. So if I assume that it's a steady state where the fluid is actually flowing at a constant pressure drop, then it's fair to assume that the pressure gradient is constant. Then these three equations are similar modulo a constant which is dp by dx. So it's fair to assume in reality that the pressure gradient is known because I have a pump which is actually flowing the fluid. So it's a measurable property. So if I know what the pressure gradient is, I am done. So these three equations are very similar, which means that if I know the solution of one of them, I should be able to guess what the solution of the other two equations are, because they are structurally similar. So a right way to put that is, suppose I say that the velocity u star is a function of, okay, x star. Naturally it has to be a function of x star and y star, because you have x component velocity which is varying in both x and y, and it has to be a function of the Reynolds number because that's the property of the fluid which is appearing in the equation, and it has to be a function of dp star by dx star. Okay. I haven't solved the equation. Note that I have not solved the equation. Which one? Yeah, it's a constant, but still it should be a function, right? The constant can be different numbers depending upon your system, but it has to be a function of that constant. Okay. Yes, it is a constant, it doesn't change. So without solving, I have simply assumed that it's a function of these four quantities. Okay. Now what do we want to find? The purpose of writing these balances is to quantify these processes, right? So if I want to quantify the process, the momentum diffusivity is quantified by the friction coefficient Cf. So remember that we defined three quantities. One is the friction coefficient, the other one is the heat transport coefficient, and the third one is the mass transport coefficient. So the objective of the exercise is to find these three coefficients. So if you want to find Cf, it is defined as, what's the definition of Cf? Okay, it's mu du by dy at y equal to 0 divided by rho u square by 2, right? So that's the definition of friction coefficient. So now if I convert this into dimensionless quantities, so that's mu, the scaling for u is capital U divided by L into dou u star by dou y star evaluated at y star equal to 0 divided by rho u square by 2, right? So now you can rewrite this as mu by rho into 1 by ul into d u star by d y star at y star equal to 0. What is mu by rho into 1 by ul? Is 1 by Reynolds number, right? So this is nothing but, oops, I forgot a 2. So that will be 2 by Reynolds number into dou u square by dou y square, y star equal to 0. Okay. So if u star is a function of x star, y star, Reynolds number and dp star by dx star, what about Cf? Cf will be same thing, evaluated at y star equal to 0. So remember that you take the derivative of this and evaluate at y star equal to 0. So the dependence on y star is gone because you are actually evaluating at y star equal to 0. So which means that this should only be a function of x star, Reynolds number, and dp star by dx star. Why? Because you are evaluating this function at y star equal to 0. So you are removing the dependence on y star because you are interested in the friction coefficient at the interface. That's what we want to know. So the friction coefficient is now function of only x star, Reynolds number, and dp star by dx star. So supposing we perform the same exercise for the heat transport coefficient. So note that again, because these three equations are similar, so T star will also have the same functional form, except that it will now be a function of Prandtl number and dp star by dx star. Why is it function of dp star by dx star? Because velocity appears in the convection term. Okay. So therefore T star is now a function of all these 5 quantities, x star, y star, which is the dimensions, Prandtl and Reynolds number, which is appearing as a scaling in the diffusion term, and dp star by dx star are it's the pressure gradient. Okay. So heat transport coefficient is defined as minus kf dt by dy divided by Ts minus T infinity. So now if I introduce the non-dimensional quantities, so that will become minus kf T infinity minus Ts divided by L T star by dy star at y star equal to 0 divided by Ts minus T infinity. What is that? So that is, so this cancels out with a minus sign, and so that will be kf by L into dt star by dy star equal to 0. Okay, all I have done is I have just cancelled out these two terms and pulled the minus sign inside, and so there will be kf by L into dt star by dy star. So this equation we can now rewrite as h into L by kf, that's equal to dt star by dy star, y star equal to 0. Okay. Now this is only a function of, because you are evaluating at y star equal to 0, so this is only a function of x star, Prandtl number, Reynolds number, and dp star by dx star. Okay. What is this? HL by KF? Nusselt number. So this is what is called Nusselt number. I am sure you must have seen this in your transport course the last semester. What does it signify? So this is L by KF into A, which is the area of heat transport, local area of heat transport, divided by 1 by h into A, right. So you can rewrite it as L by KF into A divided by 1 by h into A. What is L by KFA? That is the resistance for conduction in the fluid. Okay. So that is the resistance for conduction in fluid divided by the resistance for, what is 1 by HA? So it is the resistance for convective heat transport. So note that here convective heat transport means what is the extent of transport of heat because of the presence of convection from the solid to the fluid phase. Okay. So here we are not referring to convection because of the flow of the fluid. Here we are referring to what is the extent of heat that is transported from the solid to the fluid phase in the presence of convection. Okay, so that's what it signifies. Now note that it appears very similar. The functional form or the quantities look very similar to what you saw for the Biot number in conduction. What's the difference? So in Biot number, it's the conduction of the solid. So here, there you are comparing the resistance to conduction in the solid versus the resistance to heat transport because of convection from the solid to the fluid. Here you are comparing the resistance of conduction in the fluid phase versus the resistance for transport from the solid to the fluid phase. So there is a fundamental difference in the quantities, and that's why they carry different names. Okay. So now one can actually do the same exercise for mass transport. So if I call this Ca, okay, instead of Prandtl, I replace it by Schmidt number. Okay, that will be Hm, Dab, that will be Ca, and Cas, Ca infinity. Okay, so I can do the same exercise. So this will be DAB and DCA star by dy star evaluated y star equal to 0, and this will become, what's that number? Hm DAB DCA star by dy star, and that's a function of Schmidt number. What is this number called as? No? So this is called the Sherwood number, if you have not heard of this. So it's the Sherwood number, which is Hm into L by DAB. Once again, it defines the ratio of the resistance to diffusion, mass diffusion in the fluid phase, divided by the resistance for mass transport due to the presence of convection from the solid phase to the fluid phase. Okay. So you can see that without solving the equations, so note that we have not solved anything. So all we have done is we have introduced some approximation simply based on intuition as to how the fluid flow is behaving in the boundary layer, how mass transport and heat transport would occur, and we are able to come up with some really comprehensive numbers which sort of characterizes the heat mass transport and momentum transport in the boundary layer. Okay. So we'll stop at this point.